In this video, we will discuss the properties which can be obtained from the stress and strain diagram. Properties such as modulus of elasticity, elastic and plastic deformation, yield point, ultimate tensile strength, Poisson ratio, resilience, toughness, anelasticity, and we will also see the representative stress and strain curves for different materials. So here this figure shows the stress and strain curve obtained for the mild steel during uniaxial tensile loading. A separate video is there in which all important points on the stress and strain diagram has been discussed. So the first property which we can obtain from the stress and strain diagram is the modulus of elasticity, which is the ratio of the value of stress and strain within the elastic limit. So here B is the elastic limit. If you take the ratio of the stress and strain, then you will get the modulus of elasticity. Modulus of elasticity is physically it indicates stiffness or rigidity of the material, which implies the resistance of the material towards elastic deformation, and which in turn is related to the atomic bond strength of the material. So there is also another term which is shear modulus. So if you are applying shear loading to the material, then ratio of the shear stress to the shear strain is known as the shear modulus. Then we have bulk modulus. If you are applying pressure and that pressure is changing the volume, then ratio of the change in pressure to the volumetric strain is known as the bulk modulus. So we have elastic deformation. So elastic deformation means when you remove the external applied load, then material comes back to its original state. This is known as elastic deformation, which is in the stress and strain curve is shown by the elastic strain. The plastic deformation is the permanent deformation, means when you remove the load, the material does not come to its original state, and there is permanent strain or permanent deformation in the material, which is shown in the stress and strain curve by the plastic strain. Here you can see in the stress and strain curve that when you move from point E to point F, you require a higher value of stress for producing strain. This region is known as the strain hardening region, means strain is hardened to produce here, and the reason behind the strain hardening region is the dislocation pileup or dislocation pinning. So when there is a dislocation pileup, then you need higher value of stress or externally applied load in order to move the dislocations for producing the plastic deformation. Then we have ultimate tensile strength, which indicates the maximum value of stress sustained by the material during tensile loading. And at ultimate tensile strength, necking starts. Ductile material shows necking, likewise is shown here in this figure, whereas the brittle materials do not show necking, and there is a very less plastic deformation, and in brittle materials there is sudden failure of the material. Then we have Poisson ratio. Suppose we have this bar. If you pull this bar from both of its end, then what will happen? That its length will increase, but simultaneously when its length is increasing, its diameter will also decrease. So there will be an axial strain, means along the axis of this bar, and there will also be a lateral strain. So if you take the ratio of the lateral strain with the axial or the longitudinal strain, means change in the diameter with the original diameter is the lateral strain, and change in length with the original length is the axial strain. If you take this ratio, then this ratio is known as the Poisson ratio, and here negative sign shows that when you apply this tensile loading, its length will increase but its lateral dimensions are decreasing. So that is why for mentioning that a negative sign is taken here. For real materials, the value of Poisson ratio lies between 0.25 to 0.4 with an average of 0.3. So generally Poisson ratio, if it is not given, we take the value equal to 0.3. Then we have resilience. Elastic deformation we all know. So if you take the area of the stress and strain curve up to the elastic limit, then this is known as the resilience. And modulus of resilience is the area under this stress and strain curve. So here if you can see, this is a triangle, and area of this triangle is the 1 by 2 base into height. So base is this strain value, height is the stress value, and we all know that the There's a relation between stress and strain according to the Hooke's law. So if you put the value of strain equal to sigma over E here in this equation, then you will obtain the modulus of resilience equal to 1 by 2 into sigma square over E. So modulus of resilience actually it represents the largest amount of strain energy per unit volume the material can absorb without causing any permanent damage to the material. Means within the elastic limit, how much energy can a material can absorb, that actually signifies the resilience of that material. So from the designing perspective, it is important in designing of bumpers or shock absorbers. Then we have toughness. So toughness is the ability of a material to absorb energy until it fractures. So there is a modulus of toughness which represents the area of the stress and strain curve or area under the entire stress and strain curve. So if you take the fracture point and you will calculate the area under the stress and strain curve, then you will obtain the modulus of toughness. Brittle materials has less toughness in comparison to the ductile material. Likewise, it can be seen from this diagram, like area under the stress and strain curve is larger for ductile material and it is less for the brittle materials. So from the designing perspective, it is important for the materials which can be accidentally overloaded. So we can take this into account. So where if there are chances of increase in the load, then sudden increase in the load, then we can choose for that application the material which has higher toughness. So toughness can be changed, toughness and resilience both can be changed by alloying. So researchers use different alloying metals for increasing the or for tweaking the resilience and toughness value. Likewise, if you change the carbon percentage in the steel, you can change the toughness value. Here you can see we have soft steel which contain up to 0.1% of carbon. If you increase the percentage of carbon up to 0.2%, you have structural steel which has less toughness value, and hard steel has higher carbon percentage. So it has the, here you can see it has the lowest toughness value, but it has the higher resilience value. So by increasing the carbon percentage, the toughness of the steel decreases. So energy absorbed by the material up to the fracture is known as the toughness of the material. Then we have anelasticity. So it is a special case of elastic behavior. So if you have elastic component or if you have the elastic strain component which is time dependent, then we have this phenomenon of anelasticity. So when you in elastic deformation, if you apply the load and after you have a fixed value of load, then if elastic deformation is still continuing after that fixed value of stress, then it is known as the anelasticity. So in addition to that, after a certain application of stress, the elastic deformation is increasing, and after the removal of the stress, if the material require some finite amount of time for the complete recovery to its original state, then it is known as the anelasticity. Likewise, in normal materials, what we study that if we remove the load, the material comes back to its original state immediately. But there are some materials, if you elastically deform them and if you remove the load, the material will take a finite amount of time to return back to its original state, and this phenomena is known as the anelasticity. So it is a time dependent microscopic atomistic processes which actually plays a role in this anelasticity. So metals do not in metals the unelastic component is very small, it is often neglected, but it is higher for the polymer materials, and for polymeric materials anelasticity is termed as the viscoelastic behavior. So if there is a time dependent strain component within the elastic limit, then those materials are known to have the property which is anelasticity. So here these are the representative stress and strain curves to give you an idea about the properties of different materials. Likewise, here you can see polymers. Polymer can sustain a very low value of stress, but they will have higher value of strain. So metals will have higher value of stress, means they can sustain higher value of stress in comparison to the polymers, whereas ceramics can sustain higher stress value in comparison to the metals, but the strain which is obtained during for ceramics is very less. So that is why ceramics are brittle while metals are considered as ductile. And here this is the example of steel. So here the cast iron has higher percentage of steel, whereas mild steel has lower percentage of cast iron has higher percentage of carbon, whereas mild steel has less percentage of carbon. So the mild steel is ductile, whereas cast iron is brittle. And if you do the tensile testing or stress strain curve, if you will obtain for concrete, you will get a this type of curve which shows less strain in comparison to the mild steel. So there is also a temperature dependence for some materials. Likewise, if you take iron and if you test it at room temperature, you will obtain a higher value of stress. But if you change the temperature to minus 100 degrees Celsius, means you take the sample, you put it at minus 100 degrees Celsius, and then you perform the tensile testing, then you will obtain that the strain value is comparatively decreased and the stress which the material can sustain has increased. But at minus 200 degrees Celsius, there is a sudden fill in the component in the specimen. Here strain value is very less, but the load with which it can sustain is very high. So here what is happening, that iron is changing from the ductile region to the brittle region, means it is iron is supposed to have the ductile nature. Likewise, mild steel is known to have ductile behavior, but if you lower the temperature of the mild steel specimen and then you perform the tensile test, then the material becomes brittle. So it is known as the ductile to brittle transition. So this was all for the important points or properties which can be obtained from the stress and strain curves. Thank you.